Okay, we are happy to have Eva coming all the way from Ithaca to tell us about ability and learning in strategic interaction.
So thank you all. And I guess, this is a pretty mixed audience with some people over there knowing too much and maybe other people knowing less. So if I'm going too fast, please interrupt me and ask questions. That definitely does improve things. So don't hesitate to ask. So, I have been working on this area, which is often called the price of energy, for quite a while now. And I guess what the general question we're trying to ask is, when different agents interact, all selfishly optimizing for themselves, what can we say about the global outcome? And, the bad news is, what we can say about the global outcome is that it's horribly bad to every single one of them compared to what they could reach if they only cooperated on what to do. And the good outcome is when you can say things like, oh, it's not that bad. We don't have to coordinate globally. What I've been most interested in the last recent years is go away from this classical definition. So one thing you have to ask, what do you mean? What happens when people interact? What's the outcome that you expected to happen? And the classical answer is that the expected outcome is the Nash equilibrium, is a solution where no one wants to change the outcome. And I guess recently I've been more interested in, who told them to find that Nash equilibrium? What if I instead make the assumption that they reach learning? So these are repeated games, and people are learning to get the right outcome, to get good for themselves. Selfishly optimizing using some sort of learning algorithm. The questions one should ask here is, what the hell do I mean by learning? What form of learning might be good for them? And what can we say about the global outcome when everyone is using whatever we agreed is the right form of learning? My favorite example in life, which is what I originally started to work on, is always traffic routing with delays, which could be car traffic on highways, or it could be packet traffic on the internet. I guess a very simplistic model here is that the routers are doing our damnness to find the shortest path, the drivers doing their damnness to find the shortest path to where they're going, but that the time it takes to get across someplace depends on the congestion. If it's routers, then there is delay because the routers have to send one packet at a time. If it's cars, then I guess we have experience with this. The sort of classical or the old work with Tim Ravgarden now more than 20 years ago is trying to say that, we can say something about the Nash equilibrium. I guess this is the form of the theorem that if you take the Nash equilibrium with traffic rate Ri between sourcing destinations I, and compare it to a centrally designed optimum.
I is the factor by which you slow down when the...
I is just an index of where source destination of people. So some people want to go from the Institute to New York City, other people want to go from Rutgers to the Institute, or whatever people want.
Anyway, I meant it's a linear model. It's a
convex model. It's not actually linear, because the delay is a function of the congestion. The time it takes is a function of the congestion. The assumption is simply that the delay is not even convex, that it's continuous monotone increasing. So more congestion, more delay, and it's happening so in a continuous way. If it's convex, then it's a little bit nicer, because then you can optimize over it, but the theorem applies even if it's not convex, as long as it's continuous and monotone. The price of energy was defined actually not like this. It's a worst case Nash equilibrium over the social optimum. From that perspective, you can view this theorem as a cheat, because we're comparing to the optimum with twice the traffic rate. But I actually prefer it, and for this talk I will offer a different result in the same vein. Is what it's asking is how much you should up the capacity, or how much you should make this system bigger to accommodate it, despite that they're going to be selfishly routing. So what this says is that if you actually design the system so in centrally designed could accommodate double the traffic rate, then you'll be okay if people are selfishly driving. So I like this sort of capacity expansion view of this word. There is less work on that direction. There's tons and tons of work on price of energy, both in congestion or traffic routing style games or things where congestion is causing troubles, and in auction style games. I'm not going to go through any of it. Trust me, there is 20 years of beautiful work here by many people, including some in the audience. What I'm going to ask you is, what's up with this Nash equilibrium? And I guess, remember, Nash equilibrium was a state of the system that is a choice for everyone of what to do, such that for everyone, given what everyone else is doing, this is what you're doing right now is your best response. That's a Nash equilibrium. It has a lot of troubles. I guess there is the classical ones that even economists tend to accept as actual troubles. How would the players know to play this Nash equilibrium, especially if there are many of them? Then how did they choose to coordinate on one? There is a lot of information needed. You need to know who the other players are and what the hell are they doing to get this. And then there is the CS objection that in many games, actually not in traffic routing, but in most games, it's computationally hard to find the Nash equilibrium. So you could say that maybe there is something wrong here. Instead, I want to say they're learning. And this is a maths institute, so maybe I can admit that I'm secretly still a mathematician. My PhD is maths. This is a mathematical model of learning, no matter what we do, is, these are going to be the iterations. Every iteration, every player does something. This goes on over time. One hopes that over time you figure out what's good for you. And here is one version of learning that we all learn to love, called no regret learning. And I guess in English, what no regret learning says that you should expect to, or should want to do at least as well as a single strategy with hindsight. So they're not asking you to use the same strategy all the time. Learning is actually not like that. You want to figure out what, you try this and that and figure out what's bad. But if there is a single strategy or single action X, which is really good, please do at least as well as that one. So your utility should be this is utility of player I. A is the vector of actions, so everyone else did here. Actually, I should point this way, right? Yeah. Utility of action. This is the notation for utility for player I. If he were to do action X and everyone else would do what they did, minus a little bit of error. This is sort of a learning error. Like, if you're learning in the beginning, you don't know what you're doing, so it can be that good. But this is a notion that became super popular and still is super popular. It has two giant advantages. I think of this as a behavioral model. That is, I can say that someone learned, must have satisfied this condition. If there was a single thing, like you're driving, I don't know, maybe you come from New York all the time. Maybe there are multiple rats here, though I'm not. I think there are multiple rats. Every morning you do something. If there is a rat that's always shorter than the other rat, you really didn't learn if you don't do as well. You might do better than this. You might know if it's raining, you should drive on this rat, or if it's not raining, you should drive on the other rat. Or if the sun is very strong, you should do this, and the sun is weaker, you should do this other thing. Maybe. But if there is a single rat that's always good, and you didn't figure this out, you don't do it as well, then you somehow didn't learn, which is what I meant as a behavioral model. And second, there are very many simple algorithms that achieve this path. So it's algorithmically doable and humanly maybe explainable, and maybe that's why we like it. Actually, secretly, that's not why we like it. We like it because it's a theory condition that's super easy to use in proofs, or nice to use in proofs, and in fact, it worked very well. So price of anarchy has been defined by Koutsoupias and Papadimitriou in 1999, and then there was a sequence of papers that said, no, actually, it doesn't have to be Nash. if everyone is learning and everyone is a no regret learner, that is, everyone satisfies this no regret condition, then it applies the same bands on almost all games, applies also on learning outcomes. Here it is. I guess I like to credit originally with a Blum, Hagiati, Liggett, and Ross paper from 08, actually original version a bit earlier. And then there's a beautiful summary of Tim Roughgarden that really highlighted that this is a very general phenomena here. And what it says that they actually called it price of total NRP, but the bands are the same. So let's just call it price of NRP. That the same band extends, and here is the, oh, sorry, I didn't mean to do that. Where am I going? Yes, here is the form of the band is the outcome over all the iterations, so time 1 to capital T with some big enough capital T, sum of the utility of all the agents. This is the same game they're playing, so the optimum now went up T times because they're playing it T times over, and I take the limit basically to wash out the error term due to learning mistakes. We even extended it to all kinds of other things like dynamically changing population, not assuming that it's always all the same players. So based on this line of work, I think our whole community agreed that, yeah, no regret is a beautiful, exact notion that we need. No regret is a natural model, it's strong enough assumption, it's a natural assumption, it's doable assumption, it's a strong enough assumption, and we can do beautiful things with it.
And the algorithms are typically multiplicative weights or update.
Follow the perturb leader or multiplicative weight. So there is if I want to just mostly talk about no regret, this was the intro part of my talk, and now I'm going to start criticizing this in 1 tiny second. But to admit the truth, there is a slight bug here. We know that in order to achieve no regret as an algorithm, you have to randomize. Deterministic algorithms cannot do this in the worst case. That's a fact. Yet, if you watch what people do in practice or in data, they do seem to reach no regret, but they're definitely not randomizing. They're using gradient descent. Gradient descent is not a randomized algorithm. It's a pretty deterministic algorithm. So they're somehow achieving the no regret condition, not because they used our algorithm, but some other reasons. And there are theorems that support this. Like if the environment's sufficiently random, then you can be deterministic. And I think that's what's really happening there. But the 2 statements I made somehow are not on the same plane. That is, I do think it's a natural condition and feel like people didn't achieve it, maybe didn't learn. And there are simple algorithms that achieve it, but these people, when they achieve it, they don't use these algorithms. They do something else. Does that make sense? And what they should do that the weight is one of them, which is randomized, follow the perturbed leader is something very similar. Okay, yeah, this was minute number something, and now you have to hear the rest of the talk, which will tell you that something is wrong here. And what's wrong is the assumption that we're playing the exact same game with no care, like the game didn't change because of what you're doing. And I guess somehow there is carryover effect in your head that is the learners affected by what happened last time, but that's the only carryover effect. That's the assumption in all this work, including ours with the dynamic population. And if you think about it, some applications, this is okay, and some are not. And I guess going back to my favorite example of traffic routing, I would say it's definitely okay in morning rush hour, no matter how bad traffic was Monday morning, by Tuesday morning, they're gone. They went home. It's a new copy of the same game. Maybe it changed. Maybe the routes got closed or new people came, which is what our dynamic model actually is trying to model. But there's no leftover cars from the previous second. But if instead to do a second by second packet traffic, it's obviously not true. If traffic was really bad, either the routers are still holding those very same packets and they're trying to send it, or even worse, they dropped it, and then the sender wants to resend the packets because it got dropped. So there is a direct carryover effect from iteration to iteration of the kind that We're not modeling when we have the results on no regret learning. And what I'm going to ask in this talk is what happens in games where there is carryover effect. And I think that's actually a sort of, general question. We have worked on two applications. In this talk, I'm going to focus on this one, which is a version of packet routing. So packets are getting sent in this very simple network for this talk. There are queues that have packets arriving at some Bernoulli random rate. There are servers here that are trying to serve the packets. If you want to get as many packets through, you should probably coordinate. So they don't do this colliding here. They don't spend the same packets. Two people sending the same packet to the same server, that's not going to have full. But I'm going to instead assume they're just figuring out by learning what to do. The model is that, which I think is true on routers in the internet, one of these routers can send one packet at a time. So even if it has a long queue, you can only send one of them, and the servers can only serve one packet at a time, which causes the congestion here. Like if the two of them go there, one going to have to get rejected. This is joint work with Jason Gaitonde, who is now a postdoc at MIT and just appeared at JCL. We also worked on a different application. So here going back here, the carryover effect is a drop packet. If I drop your packet, you're going to want to resend it. So there is drop packet carryover effect. There is maybe another more powerful or even more clear application of carryover effect is auctions with budgets. If you think of ad auctions on the internet, then when you set up an ad auction, if you were to set one up for your company, if you have one, or whatever purpose, the very first thing Google asks you is how much money you're willing to spend this month. That's your budget. And the budget is the carryover effect. If you're winning, then you have less money tomorrow. If you're losing, you have more money tomorrow. And if you look at how these people operate, or companies operate, they seem to want to spend their money. There are funny budget effects going on that I hear from people working for Meta or Google. For example, the end of the month, the ads tend to be more expensive than the next day. Like the 31st of January is more expensive than the 1st of February because they wanted to spend their money and there was leftover money in the system. So they really want to spend their money. Budget is an important thing for them. But I'm going to tell you a little bit about this, but really want to focus on the other one, which maybe is more, at least for the math side of this audience, that maybe is a more interesting application. And I apologize for the CS side that might have preferred this one. So the questions I want to ask is, we want to understand better the price of energy style results if there is carryover effect between runs. The prime question I want to induce you to think about, and I'm trying to work to induce myself to think more about, is no regret a good enough assumption or a good assumption here? And I guess the answer will be yes and no. As in, I will show you results with yes, but I'll also show you examples to suggest that there is room here for better learning. You have to figure out what is the better assumption about learning. And no regret is not strong enough here.
Is the definition even clear?
No,
Not yeah, so the definition of no regret is not even clear. Given that the game is changed.
Okay. Yes, that's a good point. What is the right notion? What is the natural notion of no regret? I guess I went for the notion of no regret that multiplicative weight achieves. So we can run multiplicative weight algorithms in this application that achieves something. Question is that good enough? Yes or no? And that will have the mixed answer, as I will show you positive results that one can prove things with it, but also room that one should be able to do better with a better notion of learning. For queuing, I will do, which is what I mostly want to focus on, I will do this dual band, that is how much more capacity do I have to give the system to guarantee that learners get across. For the liquid welfare, for the auction, there's a form of welfare that we're using in our results. And I have a couple of slides here about the welfare one, but I'm going to maybe even not really talk about them or quickly go through it. The auction version is a pretty simple auction. There are items coming with values 0 and 1, between 0 and 1. You know what your value is. You have to bid something. Your value is what you think the value is. That is the value you won minus the price you paid, but you're budgeted. That is, if you go above your budget, you're in trouble. So that's your value, assuming you stayed under your budget. There is this funny notion of liquid welfare.
Shall we read it or maybe?
You can read it if you want, I guess. So, okay, value that you won minus the price you paid is the natural linear version of what your value is, except there's a condition. If the price went above your budget, the way the systems run, they literally prevent you from bidding when you can't go above your budget. The system's preventing you from doing this. If you want it as a game theory term, I should say minus infinity if you went over your budget. You're not allowed to go over your budget. And then
What would be the budget in the
over the period.
case? In the case of Qs.
Qs, there is no budget. This is all just auctions, all just auctions. The one notion here that's really awkward is that you can't expect welfare to be high. If I have no money, like my budget is $10, Avi's budget is $1 million, then no matter how high my value is, I don't have money. Avi has money. Avi is going to win everything. And so I guess there is this funny notion of liquid welfare that's suggested, and that's what we're using, where I limit you to, don't give you credit if you win above your budget. That way, the optimum became lower. Like even though my value is high, because my budget was 10, what I can contribute to a centrally designed optimum is only 10. So don't give me too much, I don't have money. And with that notion, we're proving some welfare. I'm going to actually cheat through this. And maybe just give you sort of the higher level point with the example that I wanted to actually show you. So the higher level point is that there was a sequence of papers by Balsero, starting with Balsero and Gur in 2017, which offered an algorithm with some sort of guarantees on no regret. They have a funny condition that I put in green, which is that you get no regret, not only if you're playing this against arbitrary adversaries, but only if everyone else is doing this too. It's a randomized Bayesian arrangement. I'll come back to, or won't come back to, but there's some natural assumption of what the items coming are independent random pools for some distribution. But more interestingly, they have to assume that everyone else is doing their algorithm. Not something no regret, their algorithm. And under the same condition, there's this paper from ITCS a bit more than a year ago that says that then there is a price of energy condition. But they also point out that no regret is not a good enough assumption here. This is all second price auction, which is the sort of standard auction format that the one with the highest bid wins, but you only pay the second price. And I guess what we proved with Giannis Fikioris is that in first price, you can actually prove price of energy bands. Again, I'm going to cheat through this and not tell you much. So in first price, if you have a no regret algorithm, it achieves 2.41, some extra digits, price of energy band. Again, I don't want to spend time on this except for the example. So I want to show you what's wrong with second price. And the reason that's useful, because somehow what's wrong with second price, or what you might want to do to improve second price, is somehow cleaner in the auction setup than it will be in the queuing setup. So I thought I should show you this one. So a very simple auction example. Bad example is second price. So again, the winner is the guy that pays bids the highest amount, but he only has to pay the second price. There are two players, very similar. Everyone's valuing every item at value 1. So if you want, this is a deterministic version or Bayesian or whatever, but every value is 1. But one of them has a ton of money. so much that he can afford to buy all the items at the full price. And the other one has no money or some epsilon. But unfortunately, they're somehow both being dumb, or at least the poor guy is aggressive and the rich guy is dumb. And the rich guy is bidding 0 and the poor guy is bidding 1. Does that make sense? Okay, so the rich guy is bidding very sheepishly, despite that he's very rich, and the poor guy is very aggressive. And apparently this has no regret. Obviously no regret for the guy that's poor, because like he won everything, like how can he have regret? But weirdly enough, it has no regret for the rich guy, because what he sees is that the other guys keeps bidding 1. If I win something that has value 1 for me and I have to pay 1 for it, that's not worth it. Like, you know, value minus price, that would be 0. So whatever, it's not a useful action for me. The outcome, of course, under our liquid no regret rule is horrible, because the poor guy only gets credit in liquid welfare up to his poorness, whereas we should have given the items to the rich guy. You also might feel the rich guy is doing the wrong thing. And that's what I want to point out. Possible remedy, the player 1, that is the rich guy, should bid more aggressively to drive the other fellow out of money, because afterwards he can have all the items. And this somehow, the reason I'm showing this is this. No regret appears to be very myopic. We somehow know, given his budget, that he's going to have to react. It's not a strategy question, it's a fact of life question. Given his low budget, he will physically not be able to bid this high if I drive him out of money first, but the no regret condition doesn't know about this. This is where what the algorithms achieve is this form of no regret. Yeah.
But does the rich player know about this? They don't know the.
Yeah, good question. So a rich player might not know that the other guy is poor. Even then, you might want to bid a little bit high to see. You know, maybe you run him out of money. It's not costing you anything. You could bid higher. But this is a very simplistic example, and I don't have positive results to show you that better learning can do something better here, just so that the sort of the long-term effect thing is very clear on this example. You could drive him out of money if you tried. You're not trying. And no regret is not inducing you to try. What I really want to tell you about is this queuing example, which is maybe mathematically more interesting. At least the proof is more interesting. So here is a very simple model. There are queues and servers. The queues have some arrival rate, that is Qi has arrival rate lambda, which is like every iteration, a Bernoulli process with probability lambda, new packets show up. The servers, instead of thinking of them as perfect, I'm going to think of them as having a probability that they can serve. Honestly, this is good for the induction proof, but and will be good for my example, but if you prefer, you can make the servers perfect. The theorem doesn't actually change. So each time I said every queue can send 1 packet to a server. Like as I said, they limit it to sending 1 packet at a time, no matter how long the queues are. And then the servers can serve 1 packet at a time. So if there are multiple things show up, they need to reject it. And because of the probability, they might actually fail to serve even the one they had. Servers attempt, this is going to be important. I'm helping the system a bit on getting things through by timestamping the packets and having the oldest packet go through all the time. And I'm going to want to understand what happens in this system. Now, with a sufficiently matchy audience, maybe everyone knows the very basics of queuing theory, but just so that we're on the same page, the simplest version of this is 1 queue, 1 server. Like there's not this whole system here. This 1 queue, 1 server. There's no learning there. There's only 1 server. You're obviously going to send to that server. Everyone sends to that server. And that's sort of standard in queuing theory. Lambda and mu is the standard notation here for the arrival and the service rate of the packet. And the standard theorem here says that the Q of packets remains bounded if lambda is less than Q. Hopefully you all know or see that if lambda is greater than Q, then you can actually hope for anything. Like if packets arrive faster than the Q can clear them, then well. If there's equal, there is some awkward side condition here, and there is actually a slow growth of the Qs because of equalness, but ignore that. And if they're strictly less, then I guess it's bounded, and the bounds that we know for this are finite, but depend on the gap. The smaller the gap, the bigger the Qs get. In this talk, I'm going to sweep this sort of bounds under the rug and just say it's bounded. If it's strictly less, it's bounded. And I'm not going to also worry about equal. So every one of my theorems will have strict inequality, and I kind of know what happens if there are equals there, but let's ignore that. So again, before we can think of learning, I want a baseline measure. That is, I want to know, okay, what would happen if I were to coordinate? We'll tell them everyone what to do every iteration. And then I guess, just to think of notationally making my life easier, it would be better, it's better for me if I actually order everything so that lambdas and mu's are decreasing. This is just a notational convenience. That is, the higher up Qs and higher up servers are better than the worst ones. And here is the condition. I claim that this condition is both necessary and sufficient. So let's try to digest the condition. There is something for every K. Let's start with K equals 1. So K equals 1 says that the Q with the most packets, that has most frequent packets, there must be a server that if he's alone, he could actually get served there. That is his K equals 1. So for lambda 1, the highest arrival rate has less than the highest service rate. This is obviously necessary because even if no one else is there, he can only send one packet at a time. He probably wants to send it, if he's alone, to the best server. And if the best server is not enough to serve him, obviously he's in trouble. Make sense? K equals 2, which says that you take the best two or the two highest arriving packet rates. There are 2 of them. So when life is good, they can send it to 2 servers if they have a lot of packets backed up. They can send it to 2 servers because I'm coordinating. I'm not having them crash ever. If they send it to 2 servers, they want to have the best 2 servers, and that better be good enough. K, if there are K of them, when they're very backed up, they can send K packets at a time because there are K of them. Obviously, the best K servers are best for them. It's obviously necessary. It's not super hard to prove that this is sufficient. Again, ignoring the equals. Like it is necessary, but you should, this is a form of majorization that I'm assuming here. These are probability vectors that are majorization, this is the assumption, that connected to a doubly stochastic matrix, and then this that connects the two with a doubly stochastic matrix, and I decompose it into matchings, and I tell them to use the iterations with the right probability. It's not super hard to prove. So obviously necessary, not super hard to prove that this is sufficient. And I guess the equal similar things will happen at the equal sign, similar things to what will happen as with the Qs, that actually things grow just sublinearly, as opposed to when they're strict inequality in the wrong direction, that they grow linearly.
But what if M is very different than N, much smaller than N? You don't have matching, so you don't. This condition, I mean, there's only one server, let's say, many.
Yeah.
So you can only send one at a time. So this is still true.
This is still true. So let's actually try obvious case. There's one server at a time. I guess for notational convenience, what I mean here is that if M is less than Q, I should have wrote min K and M. Like you can think of, there's 0 probability servers all the way to the end. So the condition makes sense. If there are only one server, then what should be the condition? And actually paging back to this single server is really a good example here. They're all sending to the same queue. The total arrival rate is the sum of the lambdas. And the total service rate is mu. So if the sum of the lambdas is strictly less than mu, they will get across. And that's what this condition also says, because I really should have written min, m, and q, or should think of zero ability servers afterwards. If there are more servers than queues, the bad quality servers are not useful. They can only send to as many as they are. If there are more rows than servers, then the theorem still holds. Does that make sense? So what's sort of nice here is that if there are two, say 50%, 50 or 51, 52% arrival rates, and we have a server that's perfect and a server that's, picks up the remainder, then there's a coordination that gets them across. You alternate in sending to the better one, but sometimes you send to the less one or something. There doesn't have to be a one-to-one matching between servers and queues in abilities. They can, if they coordinate, they can get across. Okay, so you don't have to sort of see the proof, but you do have to believe this because that's where we're starting from. Sounds very plausible, right? Good. So here is what we proved for learning. That is no-regret learning algorithms. You don't need this condition. You need the condition with a factor of 2 in it. That is, the capacity of servers should be twice as big, which is very analogous to what I showed you in the beginning on the package on the delay theorem. If there's double capacity, you're okay. Clearly, or maybe up doesn't seem to be for the same reason, but yes, same sort of theorem. If you double the capacity, you're okay with learning. Jason and I proved this with this very simple bipartite system. There is a very nice extension by Hu, and Lin to general networks. But I won't, for simplicity, I will stay with our simple version. Just to foreshadow where I have the proof that something here too is wrong with no-regret learning, you also have a stronger theorem, which I'll give you a little bit of hints of what's going on with. If in some way the queue's behavior is less myopic than no-regret learning, this number here is E minus 1 over E, and what's noticeable, it's a little bit better. So what I want to show, the one theorem I want to actually show you some proof of is the first one up here, the no-regret learning one, which hopefully also gives you a sense that the factor of 2 there is tight. You really need a factor of 2 for this to work. So here is how the proof goes. We're using a beautiful and powerful theorem of Pimentel and Rosenthal that says something that even if you didn't know it's true, maybe those of you with more probability background do know it, but if you don't, I think also sounds very believable. As a process of numbers going up and down, so random sequence of numbers with 2 properties, guarantees that the numbers stay bounded in expectation. What are the 2 properties? Property number 1 is something sufficiently regular. Like, if it's very jumpy, like can jump up like crazy high, then obviously that won't be true. Like sudden jumps are really dangerous here. But ignoring sudden jumps, I guess I mostly want the second condition. If when it's high, it has a negative drift. So this is a number that's always positive. So 10, 11, 12, 4, 10, 4, 9, whatever, going up and down like this. The condition is above a band, there's a decrease in expectation. So if you're above something, you're guaranteed to come down not guaranteed, come down in expectation, and the process is sufficiently regular. The conclusion is that then it will stay bounded all the time, as the theorem we're using. What is the potential function? The potential function is something maybe natural in the system. Ignore the square root, that's a technical detail. The number of packets of tau or older summed over all taus. That's my potential function. So I take all the packets in the system that are stuck in the system right now, I'm waiting, and take the h's and add them up. So a packet h tau contributes tau here because it contributed to phi tau for 1, 2, 3, 4 up to tau. So every packet h tau contributes tau. I just added up the h's. That's my potential function. What's good about this potential function? It's certainly a random function. That's just what Pimentel and Rosenthal wanted. The sum is a random number. I guess I'm claiming that, of course, if this say banded, then every queue remains banded, because then if it's banded, then every packet only stay there for a banded amount of time for one, because otherwise single-handedly that packet will contribute too much to this function. So that's what we wanted to prove. And I guess what I want to give you a couple of slides of hints or outline for that the no-regret assumption plus a factor of 2 in slack in the capacities is enough to cause the negative drift. And then I have 2 slides to talk about the sufficiently regular condition, but like what I did for the auctions, I might cheat over those slides. There's some technical things to make sure that it stays sufficiently regular. But the negative drift is where the insight is coming from. Why do we get negative drift? And that's what will make it clear that the factor of 2 is actually tight here. You need the factor of 2 for no regret to work. So here is
The sufficiently regular comes from the bound on the number of servers.
no,
It does.
no. I'll let's come back to this. In this, the assumption here is sufficiently regular. That is, the second moment or some high moment is bounded. That's what they mean by sufficiently regular. I definitely understand that if the number can jump very high suddenly, that's why the second moment is not because it jumps often. We are in trouble. That's not going to be true. In my system, the way I define it here, unfortunately, can jump down with big jumps. I sort of feel like the theorem should be true, but I definitely can't prove it, and they don't seem to be able to prove it. That is, the upwards drift is the problem, downwards drift is not a problem, but the condition they have is regular, so we adjust it for it. Okay, here is the intuition for the part I'm hoping to get across. So what I want to focus on is a particular tau. So I look at all the packets in the system that are tau older, very sufficiently old, and tau is my cutoff. And I want to say, what are these packets doing? There are lots of them in the system. What the hell are they doing? And one option is that they're smart. They're sending it to the best servers. That's nice because they have priority. Remember, all things have priority. So then they would get served. And I don't even need that they're sending it there all the time. If they're sending it there like half of the time, I'm okay. Because if they're sending it half the time, given the factor of 2 increase in the capacity, that's good enough. The service rate is high enough. If they're sending it there at least half the time. So that's a good case. Second case, so potential function decreases a lot because the half the time they're sending it the right thing, they will get served with the right probabilities and everything is golden. If they don't, that's when I want the no regret condition to kick in. And why would it kick in? Because they're not sending there half the time. From their perspective, they have priority. The good servers are empty half the time. They would have priority and they didn't go there. You know, the other half in which they're not sending it there. They should have no regret over this. They could have sent it there and they didn't. Why are they doing it? That means, no regret means they're getting this much service someplace else. So no regret causes it, like, okay, from their perspective, given that they have priority, these good servers are empty at least half the time. As in, they're not there, there's someone less urgent getting served. So they could have served there. They didn't go. They must have regret over this, unless they're getting this much service in a different place, in which case we're okay again. So again, the 2 parts is either they go there at least half the time, in which case that's good enough to get service because I beefed up the capacity, or they leave it empty half the time, in which case, wait, they could have gone there. Why didn't they do that? Regret says that they're doing at least this well someplace else. Here is the someplace else. I'm slightly cheating because of the coordination, but that's definitely the intuition. And that's also why, okay, I had to do it with 1 tau. Of course, I do it for every tau and sum it up to get the bound. This should give you some intuition that the factor of 2 bound is tight here. Because in order for no regret to kick in, you have to leave it empty a lot of the time, enough for the no regret to be powerful. So really the cutoff has to be either you send it there half the time or leave it empty half the time. And for the first part, serve it half the time to work, you need double the capacity. And indeed, the factor of 2 is tight.
But the factor of 2 is tight already with 2 queues and 2 servers. For one
Maybe, but the example we have is one really good queue, a good server, and queues, and one very good server, and okay servers, and the dumb guys are all going for the one very good server, and competing with each other and dying. Even though they're very good and mediocre servers, then they could have gotten a lot of service there. I don't know if I can do it with 2 and 2. I think actually this band is 2 minus 1 in n. So if n is 2, then it's a lesser band. It might be true that might actually be that there's a stronger band here, if there are only 2 queues and 2 servers. The extra technical details are the bounded second moment, and I'll tell you one tiny sentence here with wanting to actually spend something else. So I need this back on bounded second moment. The reason the bounded second moment is not actually true in the worst case is that if you have a super mooper old queue, and you finally clear it, then the sum of ages jumps down with his age, which is unfortunately painfully big. So instead, we switching it to a deferred decision form of the model, where I take expectation over the number of queues rather than actual number of queues there. It's a technical detail, don't worry about it. What I want to do is actually show you the example of what way is it visible that these queues are that no regret is myopic. And which I think is an interesting example, and maybe give you a tiny hint of what is the stronger theorem we can prove. So here is the example. 2 servers, 2 queues, which is something Avi likes. 2 servers, two queues have arrival rate just above 1, like tiny bit above 2, above a half. So 2 of them is a bit above 1. There's a perfect server and a not so great one down there. You can easily agree that they don't satisfy my factor of 2 condition, because this is at all of 1 and that's only about 1.5. So I'm off. If they both send it always to the top server, so probability 1, they send it to the top server, I claim they have no regret. So what happens when they both send to the top server? They have a 50% service rate. I guess the server likely kind of alternate between the 2 of them. So about 50% success rate. Down it's only 47. It's not good, not useful. They have no regret. Obviously, they also don't get across because, I made this above a half. So there's a linear growth here happening. So they're in trouble. If one of them chooses to deviate and say 90% of the time still goes to the top, but 10% decides to be altruistic and send it to the lower server. I said altruistic because when he does this, then the other guy is alone. So I'm upped his success rate from 50% to something bigger. 10% of the time he's alone. Turns out this isn't actually altruistic. This is selfishly good for him. But no regret doesn't know this. So how is it selfishly good for him? Actually, in 2 different ways. One is because I upped the service rate here from 50% to at least 60, because the 10% he's alone or something, this guy will clear. There will be times he has no packets, and then I'm alone. But also, actually, because I'm timestamping things, my packets will tend to be older than his. So in fact, I get them better than 60% service rate up there. So the painful part is, so first of all, everything clears. This is good enough that absolutely everything clears. But you have a lot of regret. up there you get a service rate better than 50%, better than 60% actually. But yet what you did clears everything despite your regret. If you do the no regret thing, and there was only one no regret thing, the one I showed you, that's the only thing to do with no regret. That one is not, that you don't clear. This one you clear. So there was some long-term effect that you're not taking into account when you're doing no regret so what's wrong? What's no regret doing wrong? And this is actually obvious, so the question before I ever got there. What is that no regret messing up? Here is what no regret messing up. And I guess this is the answer I gave to Avi about what we do, and this is what multiplicative weight or follow the perturbed leader or any of them achieve. This is the condition they achieve. First of all, I had to change the notation. Wait, there's long-term effect here. So I can't just say utility of I for the whatever happened in iteration T. It depends on the whole history. So I now updated the definition to be honest. Utility I at iteration T given the history up to T. And then what these algorithms do is randomly try things like this X thing and figure it out if it's very good. So this is the condition they achieve. Utility of X given that the history is A all the way. So this is the explore exploit. This is the explore part. You suddenly go one time try X, back off, one time try X, back off. But the condition they achieve is this funny looking condition, given the new notation. And what we really had in mind is this condition on the bottom here. What would have happened had I always done X? But that's not what we're doing. And this is clearer to see on the auction. Had I done always X, like he would have run out of money and his algorithm would, the system would have prevented him from bidding high. But the same happens here. Had I always done this mixes thing of 90% this, 10% that, it would have had the good effect. But if you just occasionally try it, it's bad. It's 50% versus 47, so there's no effect, no good effect.
Does this notation mean that utility functions have to be defined more elaborate because they're on a full history, or it's just adding up the values of the utility function for each?
So we tried a little bit to do a sort of more general theory here. At the moment, I don't have
know what it means, UI.
So this is utility given a concrete game. Utility you get in iteration T given the history and what you're doing. So both in the auctions and in the queuing game, I know how to define it. I don't have a general theory, but that's also a good direction. So I said at the beginning that we actually have this E minus 1 over E better band, which I don't actually have time to really go into, but I'll tell you what it is. It's instead of being a learning outcome, which is what I would like to have, it's a Nash equilibrium outcome. The game, what we're defining is that every player chooses a probability distribution of how they send their packets independently of each other. We evaluate this as this induces a Markov chain of queues. Everyone's goal is to minimize its expected rate at which things are growing. Hopefully wants it to be 0. And then I take the Nash equilibrium of this game and I claim, or we claim, or we have a paper claiming that the Nash equilibrium of this game has a lower price of energy than what learning outcome had, a better price of energy. That is, it's enough to up the capacities with this E minus 1 over E factor. You don't need a factor of 2, or E over E minus 1 factor. You don't need the factor of 2. The E over E minus 1 is also tight. And here is the example on the side. There is a stupid Nash equilibrium here, where for whatever reason, the NQ cell servers, all the queues decide to uniformly randomly send to servers. So it's super symmetric. Everyone just sends uniformly random. It's an ash because it's so damn uniformly random. But as you might know, if n balls are going towards n bins, then with probability 1/e, one of the bins will remain empty. So we're wasting capacity. And that's where the bond is coming from. So this bond is tight too. The way to prove it is what's usually called an equilibrium analysis. That is somehow take the equilibrium solution and deform it in some arguments on, move things and claim that the worst case is the equal service rod that you see here. But I won't go into the proof. What I want to tell you is sort of how I think about this whole agenda. So there are some positive things we can turn to, many positive things we can learn, we can prove about players that do no regret learning. Learning players can achieve high welfare in many games. Life is maybe not so bad. But no regret can be a bit too simplistic. And I'm very interested in the agenda of what would be the other good assumption here. What I'm looking for is an assumption that hopefully is reasonably true in data, hopefully algorithmically achievable, and hopefully causes better social outcome. These are the desired that I would have here. I had an original guess when we started to work on this. In fact, that's what we wanted to prove instead of proving what we proved. That turns out to be not true. So here is just those of you with more learning background, there is a notion of policy regret, which I'll tell you in a second, maybe something about how you achieve it. But unfortunately, the way policy regret is defined was already proven not to be helpful here. So that's not the right condition. Generally, I think that multiplicative weight or any of these sort of standard learning outcomes will actually do better. In fact, might even do better than this E-1/E band. That example with the E-1/E with the uniform randomness, it's insanely unstable. Even if you start them off on this, if they're running, they're going to go away from this. In fact, they're going to coordinate. Each of them will choose a server and just go there. So that's not, that's not coming out of a natural learning. That's so unstable as a dynamical system. That's not coming out of any learning process. So one would hope that more natural learning processes do better, maybe even no regret. In this example would do better, but our other example, no regret is not doing better. But what I'm hoping is no regret that's more aware of the long-term effect. That is, you're running multiplicative weight, but your explore-exploit strategy, that is, you try something and then see how it works. Please try it a bit longer to see if it has an effect. And these algorithms here that achieve the policy regret, they do actually exactly that. That's what the algorithms do. The definition didn't turn out to be good enough for us, but I think the algorithms might be, but at the moment I can't prove this. And I'm seeing there's hopeful that or I'm hopeful that no regret algorithm with this longer explore periods, where I'm thinking of doing like doubling search, like try it longer and longer. Explore period not only can maybe get the E-1/E, but maybe actually can do better than that. Because that's super unstable. That's not a natural outcome. And I'm going to stop here and thank you very much for listening.
Thanks. Question.
Is a policy regret the same thing as dynamic regret?
Gee, I don't know what dynamic regret is, so we should compare notes. Policy regret was originally championed for possible cooperative games like repeated prisoner dilemma. And the idea is that you want to do well against the algorithm of the opponent. So want to say that I do as well as I can given whatever algorithm the opponent was playing, to get positive results, they're making some assumptions that won't necessarily be true here, that the opponent's algorithm is memory limited. There's only remembers the last K iterations of what you did. So like if you might, the opponent's algorithm might say that I'll start cooperating if you cooperated 4 times in a row. That might be his algorithm, or 5 times in a row, but that there is a limit here of how much he remembers. He doesn't say that I cooperated in the first 4 iterations is cooperate, because that's not learnable. That's what they want to achieve. And then there's a mathematically described condition on how they achieve it. 2 bucks with this, the condition they have about the limited, that your outcome only depends on the last K actions for some K of the opponent. That's not true here. And then the way they describe the condition is not enough, turns out to be. But the algorithms they do is exactly what I said. Multiplicative weight with the explore period running doubling search on the exploring period. So first try things 1 iteration, then try it for 2, then try it for 4. That's the algorithm that they run. And it seems experimentally that that algorithm does well, actually.
So for me, dynamic regret is like also a similar idea. You compare with the broader class of comparators. So instead of a fixed action, you can look at like a time varying sequence of actions. But then the regret bounds they get there are like dependent on like the path length.
Yeah, that's actually no. So that's what we use there. In the beginning, I showed you this extended result we have for dynamic population. Those are the regret bounds we use for those papers. So I don't think that's useful here. Because really what's interesting is, I think, or that's certainly what I'm sort of feel the message here is that because there's carryover effect, if your learning is not aware of the not paying attention to carryover effect, you're not learning properly. Like there is, the other guy is affected by what happens in longer iterations. If you try something in the explore exploit, classical explore exploit framework without sticking to explore part, you don't see the effect. So then, and those algorithms don't do the same thing. They don't see the effect, I think. But we can talk offline, I think. At least the classical algorithms that achieve those bonds have the same bug, that they run a simplistic explore exploit policy. And if you only explore things for 1 iteration each to see, you don't actually see the long-term effect. You have to wait to see the effect.
More questions?
So the rate at which servers clear packets, like are they independent? Is there any assumption, or making such assumptions would it change the results?
I am making the assumption that they all independently have a probability, so a Bernoulli process. Like if they get a packet with probability mu for server J with probability mu J, they clear it.
How much will this change if we have some kind of correlation?
Interesting, I don't know. Good question. Honestly, mu J for me came in because to prove anything that I did, I have to first clear sort of the oldest ones clearing, and then the next ones clearing. And I guess I need it for the induction proof. That is, the oldest one went there with some probability lambda something, I don't know. And then the younger one can use it with the remaining probability if they all didn't go there. And those, because I'm assuming that the server's playing independently, I guess this is independent. So independent was natural for me, because that's what's needed. Like I admitted those mu's are there because I need it in the induction proof. Also because the example has it. It's nicer, easier to do examples that way. And I need it in the induction proof, but all I need is the independent one. I don't know what
The
happens.
result works also when all the mu's are 1.
Yeah,
So.
yeah.
in
Yeah, but he's asking what happens if I
understand.
correlate them.
Yeah, but if they're all 1, then they are correlated or not correlated, it doesn't matter.
Yeah,
For
but if the
one,
mu's
it works
are
well.
correlated, the centralized result that you should need the mu's bigger than the lambdas, it still works. I think. I have to think this through.
But it's not-
Yeah, probably it still works, but I need to, like, one thing that worries me is that the servers are sufficient, correlatedly going down and no one gets served, then those iterations we're wasting. But I think it's still okay, the coordinated one, but I don't know if the learning one is okay. Yeah, Matt.
I wanted to ask, so like, I wasn't sure if you already hinted at this, but like, is the issue with regret that like, with policy regret, that the definition of regret is not right? Because even in the example you showed, you found a good strategy, you said you really should be using this randomized strategy, and regret is telling you that this is a bad thing. Or is it that like even with the class of learnable policies, it's just hard to figure out like what's the right class of policies you should be trying to consider in these kinds of games, or both of them?
At the moment, only the first one.
Okay.
And it's not in this example. In this example, policy, like the one example I have, what I showed you, policy grad does fine. They make another complicated, like, I guess if I look at what their paper has, is a one complicated example where they do, okay, because you were experienced in this space, I'm sure you have had this experience. I worked with, at some point, with Bobby Kleinberg on something. Here's how our interaction went. I proposed a new, something that no regret can achieve, and Bobby proposed a crazy no regret satisfying sequence of actions that the players can do that fails my condition. This is something we went for a couple of months a few years ago. The example is one of those, like Bobby's example, not a natural outcome of learning. It's a crazy sequence that happens to satisfy the, like a coordinated crazy sequence, but happens to satisfy the condition. That's part of the paper. And then the other part is they conclude, which I wouldn't like to conclude, that given this, you have to cooperate. That's the only way to go. And they give an algorithm that is distributed, but if they cooperate, it can achieve better service.
No questions. Okay, thanks.